would like to thank Bob. He asked me to do the presentation on R-OTE 4.5.1, the updated version of R-OTE, which is now posted. Primarily because I've been doing the user manuals that accompany R-OTE, but he really should be the one giving this presentation as well. So, but I wanted to follow his presentation because the key part of the update to R-OTE are the improved error bars that he just alluded to. So this is the presentation on the update of R-OTE to version 4.5.1. Next slide. And some of you, I'm sure, are a little bit new to R-OTE, so I'm going to go back through the history of R-OTE just to touch on all the different versions. And so in this presentation, hopefully you'll end up with a fairly complete understanding of R-OTE. So to date, there have been 3 versions of R-OTE written. Version 3.11 was released in 2013. Then in 2014, at the next meeting, we released 3.8.2, and that version was the dominant version being used until this year, and in May we released version 4.5.1. So I'm going to go through and review the earlier versions and the features, and then introduce the new features in the latest update. Next slide. Okay, so R-OTE, because it is based on R, which is a statistically high-level statistical software language, and R-Studio, which is a interface for R, it is multi-platform compatible. So, for example, Ocular and R-OTE are Windows compliant, but they're not multi-platform. So R-OTE will now run on Windows 7, Windows 10, Apple operating systems, OS X, and Unix or Linux systems. Virtually any system that will run R and R-Studio and have a web browser. And those are plentiful because the folks that support R and R-Studio have worked hard to make it available across platforms. I can report, Bob, this morning I just got a new Microsoft Surface 10 tablet, and it runs Windows 10. And just this morning I was able to install the latest versions of R and R-Studio, and 4.5.1 is up and running on that, so we're working. Next slide, please. Okay, so R-OTE to run on a platform requires that the base program R to be installed, and R is an interpreted computer language that contains the functionality for a large number of statistical procedures that are used in R-OTE. So R-OTE is kind of like an overhead program that reaches down and pulls up all these sub-functions that are used from another language called R. So to run R-OTE, you must install R on your computer. The next is R-Studio. And R-Studio is an integrated development environment for R, and it includes a lot of productivity enhancing features and runs on all major platforms. And it provides the interface between R and your web browser. And so your web browser then is what is actually used to interact with you and R-OTE. So RStudio must also be installed on your computer. And then finally, you need a web browser such as Safari on a Mac, or Google Chrome, or Internet Explorer. So like this morning, I'm using the Edge, I think that's what it is on the Surface, to run as a web browser. So whatever web browser you want to use can be installed. Next slide. Okay, so R-OTE 3.1.1 was the first version, and it was initially intended as an upgrade and a replacement to Ocular 4.0, which was also written by Bob Anderson. Ocular is still available as a download from Brad's R-OTE North America website. And for those that are just getting into light curve analysis and you want to try the tools that Bob has developed, I recommend getting started with Ocular. Brad actually uses Ocular all the time, and we compare notes, and typically the DNR times are always almost exactly the same. Where there are a lot of differences is in the different features that R-OTE can do that Ocular can't, and I'll be highlighting those today. So R-OTE, the major difference between Ocular and R-OTE is that R-OTE is a likelihood-based statistical analysis of the light curve, and so therefore it's computationally different from Ocular, which I believe was a least squared kind of use something called a figure of merit tool to derive the DNR time. But R-OTE research identified the concept of noise asymmetry in the light curve between the baseline noise and the event noise. And you can see in this light curve that I put into this slide the concept of noise asymmetry. There's greater noise in the baseline than there is, at least greater noise intensity in the baseline than there is in the event bottom. And that's what we mean by noise asymmetry. And that's because the noise intensity is related to the actual intensity of the light involved. Next slide, please. Okay, so one of the major improvements in R-OTE is that it contains a statistically based Akaike information criterion test of the detected occultation events to determine if the event is likely real or instead more likely due to the random fluctuations in noise in an otherwise straight or flat light curve. So in Ocular, we used an ocular confidence level, and you kind of had to look at the number produced to say, well, is this a real possible event or maybe a noise event? And R-OTE, it makes that decision for you based on the comparison of the Akaike information criteria tests. Next slide, please. And R-OTE is optimized to find both clear events in high signal-to-noise ratio data and difficult events in noisy low signal-to-noise ratio data. So the top light curve is, that's pretty simple. There's an event there. And both R-OTE and Ocular and R-OTE, they'll all find an event, and they'll all give pretty consistent DNR times for that event. But when you start trying to find events like in the bottom light curve, that's a different story. And R-OTE is now optimized to identify these events. And there is an event there. Next slide, please. Another thing that R-OTE was designed to do that Ocular was not and R-OTE is not, is that it allows the analysis of gradual transitions caused by large stars, and it has even been designed to discriminate between stellar limb darkening models. So that's shown in this graphic. And then another new feature is that a test dataset generator was designed and included so that the user could generate test data files with known DNR events, known noise levels, and then use those to test R-OTE against other models, other programs, or against itself to see how well it can analyze certain types of light curves. Next slide. I'm going to go through some of these one by one as well. R-OTE includes a false positive analysis to further differentiate real events from false events caused by noise. So to do that, noise from an actual event is added to a straight line, and we do that 5,000 different times. And each run, it's like a Monte Carlo simulation, each run is analyzed to see if there are any events in this new event that was created. We use the same duration as the detected event that we detected in the analysis. And then a histogram of all the detected magnitude drops are produced and compared to the actual magnitude drop for the event that we detected. If there's a wide separation between the histogram and the detected magnitude drop, then we conclude that the detected event is not due to noise. So in this produced graphic, the red bar represents the magnitude drop of the event detected, which is the B minus A, or baseline minus event bottom value, or about 135, whereas the histogram from 5,000 Monte Carlo simulations of the same event noise placed on a straight line with the same event duration gives you magnitude drops peaking around 45. So we can conclude that this event was not due to noise. There is a false positive probability metric produced, and in this one it's 0.000, which indicates that the probability of this event being due to noise is less than 1/100th of 1%. Next slide, please. So R-OTE 3.8.1 upgraded many features. That was the next version beyond 3.1.1. It added the ability to read files directly from iMovie and Tangra. Sometimes Tangra produces blank entries, which can cause a problem. It does for Ocular, for example. And R-OTE will automatically interpolate those blank Tangra entries. Bob mentioned a Fourier filter in his presentation. That was added in 3.8.1, and that helps with the analysis of cyclical variations in the light curve that might be due to AC ripple in the video, Sometimes there's other RF interference or drift scan microlensing effects, and I'll talk about those later. And then he added the ability to use a secondary light curve for detrending the primary light curve. Next slide, please. So here's an example of the Fourier filter. The top light curve was one provided by Gerhard Nengel, where he did a study in a laboratory where he took an artificial star and then drifted it across a PC-164CEX2 camera. And what we had noticed visually in various real-life recordings is that the stars looked funny and they changed as the star drifted. So Gerhard tested that, and sure enough, you take a constant artificial star and drift it across a CCD chip from the camera, and it varies cyclically as the shape and brightness of the star changes. Well, with R-OTE, you can do a Fourier filter analysis of that. The second light curve is the filter solution for the variations in the above light curve. And then we can inverse out the Fourier filter, and the bottom light curve shows what the light curve would look like without the cyclic variation of the pixelation caused by the star drifting across the chip. So that was added, and I've used that many times to improve various light curves that we get. Next slide, please. So now we're up to 4.5.1. Bob has improved, made numerous code changes to fix little errors here and there. He has done a lot of GUI, or graphic user interface improvements that I appreciate, and I'll show you a couple of those. He's created progress bar, so a lot of times R-OTE will go out and start calculating, and it takes a long time to do some of its calculations. And on the web browser screen, nothing seems to happen. So he's created a little pop-up screen that shows the progress so that you at least know that the thing is working. The CSV files are now checked for timestamp continuity if there are timestamps included, and that helps out a lot. And then he's included an opportunity to insert camera delay and VTI offset corrections, which are necessary to get the actual real time of the DNR events that are computed. In the timing of the occultations or the cameras, he supports both NTSC and PAL. And then he added a major new feature where the primary star can be normalized to a secondary star. And I've used this feature to salvage many a very bad light curve that was damaged by clouds passing or other things that can affect multiple stars in the same video. You can normalize those out. Another thing that he did, which can be used when normalizing to a secondary star, is that sometimes a cloud will pass one star at a time different than another star, because stars move, or clouds move slowly. So he's provided a time correlation between the primary light curve and the secondary light curve so that they can be shifted and lined up. and I've used that many times. The talk that he just gave about correlated noise, that has been incorporated now, and I won't elaborate on that because he explained it already. But after we use the correlated noise, now we have square wave error bars that are user selectable at different confidence intervals between 0.5 and 0.9973, which is the 3 sigma equivalent confidence interval. And then lastly, on the light curve generator, he has included an option to integrate the generated light curve. So we can now test generated light curves that include camera integration, which is a handy way to test these solvers that we use. Next slide, please. Okay, so for graphic user interface improvements, because we're using a web browser, we have to move around from one screen to the next. And Bob has included a number of shortcut buttons now, which I use all the time, to go to different screens. So I can go to process timestamps or locate a square wave or a gradual transition edge on disk event by just clicking a different button that he's provided. Next slide, please. This is an example of the progress bar. They do pop up. Sometimes they pop up behind other windows, so you just have to be aware of that. But typically, they really help figure out what's going on and why it's taking so long for something to show up. Next slide, please. The timestamp continuity check is very, very handy. It will fix OCR errors if it can detect them, and it will also highlight blocks of missing frames. So the top one is an example of a light curve with a lot of timestamp errors, and the bottom is an example of one with no light curve timestamp errors. So it will tell you the number of OCR corrections that it has applied, and then it will also indicate the number of missing frames if it can figure that out. Next slide, please. So the camera delay and VTI offset corrections are added, but the user has to look these up in tables that I have provided in a separate paper that's posted on the Yahoo website. So Gerhard Dangle has analyzed a number of different cameras, and then for the integration, if they do integration, or even if they don't, sometimes they have camera delays between the time the event actually occurred and when it actually comes out of the camera in the video. So these camera delays can be input here in the window that Bob created, and if we put these delays into R-OTE, then it subtracts them out from the times that R-OTE derives from the timestamps, and we get accurate times. The VTI offset is a function of the VTIs also timestamp the video, and LineMovie reads those VTI timestamps for you and inputs those into the CSV file. However, the timestamp that LineMovie reads is sometimes off from the timestamp that R-OTE needs, which is the start of the field or frame. So we can put those VTI offsets in there as shown. And then down below that, it shows highlighted in red where those corrections are put into the report that comes out of R-OTE. And then the times that at the end of the lines there are the actual times that R-OTE reports. Next slide, please. This is an example of normalizing a primary star to a secondary star. And my title says a Jupiter Phimu event, but I actually put in a different light curve there, so those don't line up. But what I have there is for a square wave event. The top is the original primary light curve. The middle is the secondary light curve, and both the top and the middle are affected by cloud events. And then the bottom curve is the top light curve normalized to the middle light curve. And you can see now, with a lot of noise, there is a square wave event there. And this came from one of our many observers out there in R-OTE land. And so we can salvage a lot of the occultations from damaged light curves due to clouds and other events. Next light curve, please. This one shows the correlation, the time correlation test that Bob does. And the top one doesn't show all the little bars for me here. I don't know what you guys are seeing there at the conference. But the top one is a zero lag, because there's a little bar right there at 0 showing between the primary and secondary star. There's no lag between the time correlations of the different light curve fluctuations. But the bottom one shows a lot of differences in the lags, with a peak at around 8 frames, positive 8 frames. And so in R-OTE, I can input that number 8 into a correction, which will actually shift the two light curves relative to each other to offset the fact that it takes about 8 frames for the cloud to change the light from one of the stars to the other star. Next slide curve, please. Now this is what Bob talked about this morning, and so I won't go into it in great detail, but the 4.5.1 includes the correlated noise effect that Bob discussed on the error bars. So next slide, please. And he showed this slide with the different noise, with the top line being no correlation, the middle one being some correlation, and the bottom one being temporal correlations, similar to what we see in many scintillating light curves. Next light curve. Next slide, please. And then this slide shows the effect of the correlated noise on the error bars. The black mass distribution, or histogram, shows with no correlation, and the red distribution shows what happens when you have correlated noise, and it really spreads out the error bars. This is a distribution of errors in a Monte Carlo simulation. He did 1 million Monte Carlo simulations, and the only difference is that in one the noise is not correlated, and the other the noise is correlated. So when you try to find the error of the D and the R in the event. And if you're trying to do it at the 0.9973 confidence level, which Steve Preston has requested that we do, that's about 3 sigma equivalent. You can see that the red distribution really spreads out the degree of where your errors can occur at the 3 sigma event confidence level. Next slide, please. And then Bob showed these graphics. So the top curve, these were all generated light curves. The top is the idealized light curve. The middle one has Gaussian noise but no temporal correlation. And then the bottom one has the Gaussian noise with temporal correlation. And then they produce radically different error bars, which I'll show in the next slide. Next slide, please. Yes. So here's kind of what happens is that I have in the previous light curves I did analysis, and across the top I show there are 3 different error bars that we analyze: the 1 sigma equivalent, the 2 sigma equivalent, and the 3 sigma equivalent. So for the Gaussian noise only, we see, for example, that the 3 sigma equivalent error bar was 4.65 frames. But if we add scintillation noise to that light curve, at the 3 sigma equivalent, the error bar is now 11.95, or the ratio is about 2.57 bigger. And so that's quite a big difference, and that was the major improvement in R-OTE 4.5.1, is the ability to now analyze the effect of scintillation noise on our error bars and do it in a statistically correct manner. Next slide, please. So these square wave error bars are now user selectable at the 1 sigma, 2 sigma, and 3 sigma confidence intervals, or any user selectable confidence interval between those points. Next slide, please. And then I mentioned that camera integration can be simulated in generated light curves. This is an example of that integration simulation. The top one has no integration, and the bottom one is the same exact light curve, but simulating an integrating camera. Next light curve, please. Next slide, please. This one is with 8-frame integration. Next light curve, please. Okay, so where can you find R-OTE? It's provided in a zip file. It's on Brad Timerson's website. So you go to IOTA North America website. You just click on this and you'll get a zip file. And then in that, it includes a release package that has a standalone user manual. It's in CHM format. You have to open that separately. There's a README file that helps you start it up. And then there's a folder of test files and that you can use for testing. And then all the different files that you need to run R-OTE after you've installed R and RStudio. Next slide, please. So R-OTE is a multi-purpose tool for analyzing occultation light curves. It's the latest correlated error bar improvements in R-OTE make it the most advanced and complete occultation time extraction program available to amateurs. The large variety of features and complexity of the graphic user interface in R-OTE make it a little more difficult for beginners to learn. So if you're just starting out, Ocular or R-OTE are probably better, easier tools for beginners. But if we want to calculate error bars that are statistically correct, we need to use R-OTE for our future analyses. Next slide, please. So I've been working with Bob now for many, many years, and I think you can tell by the quality of the two presentations that he gave at this conference that working with him is a true pleasure, and I want to thank Bob for creating and improving R-OTE. So thank you. I think we're all done. So yeah, the question is, should we just double our error bars as a good start? And Derek, the answer is no, because if you didn't have a lot of scintillation and autocorrelation, you'd be producing error bars that are twice as big as they should be. So what you want to do is produce error bars that are consistent with your actual light curve. So if we think that error bars are critical, and right now Dave Harold is not using the error bars in Occult 4 to fit his profiles. I imagine that sometime in the future he will. If we want to have very good error bars to help in that fitting process, and they're critical, and you don't have R-OTE, you can just send me the CSV file and I can run those for you and get you the proper error bars using the DNR times that you want to use. Okay, so I'll release back to you guys.